region. Thanks a lot.
Okay, yeah, thanks Enrico. Thanks to the organizers for having me. So I'm going to talk about integrals, and specifically I'm talking about integrals beyond the conservative region. And this talk is based on a paper we wrote earlier this year together with Julio Parra-Martinez and Mao Zheng, and also some work which is currently ongoing together with Enrico. And this is in principle the first part of two talks, and for the second part you should watch Julio's talk tomorrow. So let me quickly introduce what we're after here. So so this talk is going to be about precision. Precision will be very important in the future for next generation gravitational wave experiments. And what has been seen already in the last few instances also of this workshop is that that amplitude methods are very powerful to obtain observables for classical gravity. And in particular, there has been some very also very recent results for multi-loop, so higher order corrections in Post-Minkowskian expansion. And the spirit of this whole endeavor has always been to use methods from perturbative QCD to have an efficient method to evaluate these things. So let me quickly explain to you the pipeline we are looking at here. So we'll start off with some QFT. This can be GR. In our recent paper, we studied n=8, which is quite a nice proxy model. You could also think about other theories like QED. What you then do is you apply amplitude methods, which are really powerful here, like generalized unitarity, double copy. Could also do it by Feynman diagrams. You will then get a loop integrand, which you have to integrate somehow. There's also methods available for this. And then finally, we get an amplitude. And from this amplitude, you then want to extract the classical physics. And I would say that this last bit, it has been fairly good understood by now. So this is something that only developed in the recent years. And there's a variety of methods that you could apply here. This first bit was basically what started off this whole thing that we can do this computation of integrands basically very efficient. And I think it's fair to say that here in the future, although this is a very hard problem, the methods that we have at our hands are so efficient that this will not be a problem in the near future. And what will really be a main bottleneck will be the integrals, so getting the integrand from the integrand to the amplitude. Just some quick thing, which I'm basically obliged to bring up in this point. There's also some other nice way to compute integrands, which is by using numerical unitarity. And we just recently published our code for doing this. And this code we use to compute the two-loop for graviton amplitudes, the full quantum, that is, which is a much harder problem than the classical physics. And you should look out for this, and in the future we will definitely use this to get some state-of-the-art computations there. So how do the integrals look like? So as I said, the integrals are the complicated bit, or one of the complicated bits here. The integrals are common to all approaches. In some approaches, you may avoid some of them. We are looking at 2-to-2 scattering with masses, so we have 4 scales in the problem. And a typical integral looks like this box integral here. Already at 2-loop, you run into troubles if you try to evaluate these integrals, the full integrals. For example, you find that not all the integrals are available in the literature, and you find very nasty stuff like elliptic integrals. So you should really ask yourself if there's any way to avoid all these troubles, and because eventually we are only interested in some very simple piece of these integrals. And indeed, there's some method which has been worked out by Byrne and others in their very nice paper. And they introduced the method to compute the potential region part of these integrals, which is one of the pieces that is interesting in the classical limit. And what they propose basically is to do a series expansion in small velocity, and then we sum the series to get some relativistic expression back. this method works very nicely at two loops, but there are some drawbacks to this method. For example, you cannot compute IR divergent integrals which appear in the calculation. So you have to manifestly cancel them with other integrals that appear in the EFT matching. Also, the series expansion, it relies on knowing basically the set of functions that can appear in the problem, and this can also lead to a problem if the function space gets larger at higher loop order, and also some conceptual problems with the fact that the approach is in some intermediate steps not manifestly Lorentz invariant. So what we proposed here is that instead of using this machinery, we should try to look something that looks more of the approach that we would use in perturbative QCD. And there is something that is quite a natural way that we would apply in this case, and it is to use the different method of differential equations together with the method of regions. And this is because the problem has a very natural hierarchy of scales, which is that the angular momentum is really a macroscopic object. So it is very large. And if you translate this to the momentum transfer, which is the natural variable we are looking at in this problem, this means that this momentum transfer has to be smaller than all the external scales, basically, all the this large scales. And then there's this method of regions by Beneke and Smirnov, which we can use to get expansions of the integrals in the limit of small q. And for this, we have to look at the different regions of the integral. And there's two relativistic regions for this integral. There's one region where the loop momenta are hard. And this in general corresponds to short-range physics, UV, randomization, and all these things. So this is not really interesting for us in the classical physics. And also, if you see quite easily that this does not contribute to the classical physics, because it will always produce only analytic contributions. So what we're really after is the region where the loop momentum is small, and it is parametrically of the same size as the momentum transfer. In principle, we could go on then and further split this region. And in particular, what we have done in the past, and what is also done by Bern and others, is that you can split the soft region again into a conservative and a radiation region. But this introduces some problems. And again, here we propose to just keep the soft region intact and do not do this splitting. The pros of this are that you will naturally also get the dissipative effects, because the potential region was basically excluding all the radiation. This approach is manifestly relativistic, because the splitting of those two regions is a relativistic splitting, so you don't have to use the resummation method. It's also quite straightforward to use dimensional regularization in this context, so you can compute actually those IR divergent integrals, and there's also some conceptual points with computing divergent energy integrals, which do not have to be done in this context. Also, something that is very nice is that you avoid some artifacts that you get from splitting the regions, which go under the name of tail effects. Of course, there's always some price you have to pay, and in this case, the problem, one of the problems is that you have to include additional diagrams. The main families of diagrams are this self-energy diagrams and this mushroom type diagrams, and those we need to supply in addition. And I think Julio will tell you a bit about this in his talk also. Another point is that we need a more general way to extract the classical physics, which goes beyond the potential matching in the EFT. Fortunately, many methods are already able to do this. For example, you can use the Kosovo-Maybe O'Connell formalism, which we use, or you can use icon resummation, which I think will be the topic of the talks of Heisenberg and Veneziano. Just quickly to explain to you how this KMO formalism looks like. So the idea is that you start with some observables, and these observables, if you pick them up appropriately, will have a smooth classical limit. And for example, one observable that we also looked at together with Enrico, Julio, and Mauro is the radiated momentum. And if you look at this, object that you need to compute, it is actually just a cut amplitude. So in general, the most general integrals that we need to compute are virtual integrals and integrals with cut, which come in this KMO formalism. So how do we actually compute the integrals? So there's a very nice parameterization for this problem, which manifests the Q scaling of the integrals. If we use this parameterization and do the soft expansion at the integrand level, we can see that all the matter propagators basically get turned into linear propagators. And in that way, we can factor out the mass scales from the problem, which is already nice. And there's only a single a single scale which has mass dependence, so we can fix this by dimensional analysis. And finally, we only get an integral which depends on a single variable. And this is a statement that is true to all orders in the post-Minkowski expansion. Just to get back to this integral we were looking at before, the box integral in the soft expansion just looks like this. A more general integral can be reduced by integration by parts identities, which is also a standard tool from perturbative QCD, to a set of master integrals. So there will always be a finite basis of these integrals that you need to compute. This is something that is implemented in various computer codes. And finally, we have to compute the single scale master integrals by differential equations. So this is what I will explain now. So the method of differential equation is split into various steps. So you start off by computing the differential equation, basically by taking derivatives of your basis elements. And then due to the fact that you had a basis and you can project the derivatives back into the basis. There's some step which you in principle don't need, but which is very helpful in practice, is in that you find a good basis for the problem, and desirable is the so-called canonical form, which I will talk about a bit later. Then you have to compute boundary conditions for the problem, and finally you have to integrate. Let me quickly introduce the canonical form. So this is a special form, a special basis of Feynman integrals, which manifests a lot of properties which has a lot of manifest properties. So it is basically written in this form, that if you take derivatives of this canonical basis, the dimensional regularization parameter will factor out. You will get some logarithmic residues, some logarithmic singularities, and in front of them you will get some matrix of rational numbers. And the nice thing is that we have a single variable problem and a single variable problem, and for this there is actually an algorithmic way to find this basis if it exists, that is. And there's also then once you have the integrals in this form, it's very straightforward to solve this problem in terms of iterated integrals. Just to give you some flavor of this, this may be a bit trivial for some people, just how it looks like at the one loop level. And you have three integrals, you take a derivative of them, you get some logarithmic term here, and then you get this simple matrix of rational numbers times the vector itself. In this case, you can perform the integration trivially to all orders in epsilon, and you find, for example, that the box integral is just proportional to this arc-cosh, which is actually related to the famous arc-cinch, which some of you, or many of you may have heard of. And then finally, we have to provide the boundary conditions, and something that we explored in our last paper is that you can use these boundary conditions to fix the region of the integral. So for example, if you provide boundary conditions in the potential region, you will get basically a resummed potential integral. So, but as I was saying, we don't want to do the potential way. We want to do the soft integrals. And also, I have to say that this is also something that other groups are working on. So there's also this collaboration by Di Vecchia, Heisenberg, Russo, and Veneziano, who has also worked out these integrals. And so we know the canonical basis for these integrals. We have actually given this already in our paper. And as I said before, there's now new integrals that we have to compute. So there's mushroom type integrals. So there's new top level integrals. The nice thing about the soft expansion is that we can now use analyticity of the results. So we can, for example, continue from the S channel to the U channel. And even better, we now have, because this is a massive problem, we have a Euclidean region for the problem. And in particular, this gives us an additional constraint that all the integrals have to be regular at basically this point, sigma equals 0. This is actually trivial at 2-loop, but gives new constraints starting from the 2-loop order. Also, we can perform, very simply perform checks. We can, for example, because those are just relativistic integrals, we can just use, for example, PySecDec to evaluate them numerically and check that our results are actually correct. And we can check that the integrals are real in the Euclidean region.
You have 4 minutes.
Okay. Yeah. So as I was saying before, there's also a second type of integral that we have to compute, and this we also worked out. So we have this cut integrals. Then there's this method of reverse unitarity by Anastasiou and Melikov, which basically bases on the fact that you can turn delta functions, or you can write delta functions as a difference between propagators. And then you know that the IBP relations and the differential equations will be the same, even though you impose cuts on the integrals. The only thing that is different will be the boundary conditions, but for this we basically have a sufficient set of boundary conditions from unitarity and from static limit boundary conditions. And to get back to the example we had before, a trivial example is this box, and here was the bubble basically, and since the bubble doesn't have a 2-particle matter cut, it's just 0 on this cut. So actually this integral is constant, and it's very simple to compute this boundary value. Okay, then let me quickly conclude. Integrals are a main bottleneck in all approaches to the post-Minkowski expansion. We have introduced a new powerful approach with the method of regions and canonical differential equations. And something that we did, and which is already partially published, is that we computed all integrals up to the 2-loop orders. So this is both virtual integrals and with cuts, and potential in the potential region and also in the soft region. And this set of integrals allows you in principle to compute all observables which can be written in this Kosovo, maybe O'Connell form. Something that is also important is that all integrals come from the same differential equation, and it's only the boundary conditions that we change always. The methods look quite up to the task for 3-loop orders and for the 3-loop order, and we actually have some results to report on, but for this you have to wait till Julio's talk tomorrow. With that, thanks.
All right, thanks a lot, Micheal, for staying on time. I guess if we can wait for some questions for Micheal. Yes, there's a question by Giulio Salvatore.
Thank you. A question about solving the integrals by the method of canonical differential equations. You mentioned that essentially you end up having a single dimensional problem. But even if you're able to find the canonical basis, you have the problem of integrating it. And I guess that in general you will encounter elliptic integrals and even worse integrals than those.
Yes.
So how would you do that?
The point is basically that up to the 2-loop order, there's no elliptics. We can just find a rational parameterization of this, and then everything is in epsilon form. So it's pretty straightforward to integrate. For higher loop orders, that's not necessarily the case. But still, you can also use this differential equation kind of in a hybrid way to compute series expansion, and then basically, if you have some idea of the solutions to the problem, you can try to fit them. Also, you would expect that the final result will be much simpler. So maybe even though you have some elliptics, they may cancel out, right?
In fact, I was asking this question also to suggest you to read a paper which was written a couple of years ago by Francesco Moriello, who suggests a method which is now implemented in a Mathematica package by Martijn Hiddink to get numerical results by doing series expansions once you have the differential equation.
Yeah, thanks.
Are there any further questions for Micheal at this point? Any raised hands? No. Maybe I ask a quick question. Are there elliptic integrals at 3 loops?
Yes.
Okay. Oh, there's one more question. Carlo Heisenberg has a question.
Yeah. Hi, Micheal. Thanks for the very nice talk. So when you said that splitting the soft region between the potential and the radiation region introduces some subtlety, you were talking about tail effects, but I was under the impression that tail effects were argued to appear only at 4 p.m.
Yeah, it's higher. It's more for future, basically. It's not relevant at this loop order. Yeah.
Okay, because we already find some, problem with the logarithm, etc. at 3 p.m. But this, I mean, as far as I understand, we were trying to interpret this as a radiation reaction, not really tail effects.
Yeah.
So do we agree with this interpretation?
Yeah. Okay. Basically, the problem was a high energy problem, right?
Also, another question: has anybody calculated just the radiation region?
I'm not aware of this. I mean, it's pretty straightforward to do it. I mean, also, I mean, you may just subtract off.
Of course, after hand, you can just subtract. Okay.
Yeah.
Thanks.
Okay. Are there any further questions for Micheal?